Hello everyone, my name is Shom Mukherjee. I am a postdoctoral research fellow at the Florey Institute of Neuroscience Mental Health in Australia. Today I'll be talking about the distribution of isomerized and racemized amyloid beta isoforms that we observe in the sporadic Alzheimer's disease using ion mobility mass spectrometry. First of all, I would like to thank the conference organizers for giving me this opportunity, and I have nothing to disclose. 50 million people around the world live with dementia currently. Alzheimer's disease is one of the most common form of dementia, accounting for 60 to 70% of those cases. Pathologically, Alzheimer's in postmortem tissues is characterized by extracellular plaques and neurofibrillary tangles. In the last couple of decades, there has been growth of different compounds that can trace the longitudinal progression of this disease in patients using PET imaging. The red dark areas that we see in the PET is actually the senile plaques, which are mainly composed of amyloid beta that are not present in the control brains. Amyloid beta is processed from a transmembrane protein called the amyloid precursor protein by the activity of gamma secretase and base beta secretase to give us the two canonical isoforms 1 to 40 and 1 to 42 A beta. This graph, taken from the Australian Imaging Biomarkers and Lifestyle Study, shows us that it takes 20 years from the onset of the disease, that is, onset of amyloid deposition, to the first clinical symptoms to occur. That means the amyloid, which is depositing in the brains, have at least 20 years to undergo different modifications, which we call post-translational modifications. And some of these are isomerization, racemization of the aspartic acid residue of A beta, along with many others. And these are actually spontaneous reactions that happen chemically inside the brains. And however, limited biochemical assessment of the exact isomers that are present in the plaques has been done so far. Before going into what we have done, let me introduce what is an isomerization and racemization of the aspartic acid residue. Normally, the native or the wild type peptides have aspartic acid residues in L-aspartate form, which in the presence of water can undergo the formation of five-membered ring called L-succinamide that after ring opening can lead to the formation of L-isoaspartate. The difference between L-aspartate and L-isoaspartate is nothing, just that the peptide chain is going through the beta carbon instead of the alpha carbon. Similarly, L-aspartic acid or L-asparagine can undergo deamidation to form this L-succinamide, which after chiral enantiomerization can form D-succinamide, which after ring opening can form D-aspartate or D-isoaspartate. So we thought these molecules which we are seeing are actually does not have any mass changes. So they are kind of indistinguishable in the mass spectrometer. And there are very few techniques such as ECD or ETD in mass spec that can distinguish between isoaspartate versus aspartate using diagnostic ions. However, recently ion mobility has been shown that they can differentiate between D and L isoforms of peptides. So we thought, let's use drift tube ion mobility. What's a drift tube ion mobility? What does it measure? Is that in the presence of an electric field, different shapes of molecules or ions in this case can move with different mobilities. That is, we call them drift time. So we theorized or kind of postulated that if we combine HPLC along with ion mobility mass spectrometer, we might be able, or rather be able to resolve the different isomers that are present in the brains. So we took a proteomic approach. First of all, we fractionated the frontal cortex of Alzheimer's as well as different controls into different pools of A beta, such as the TBS, the soluble pool, the vesicular, sodium carbonate pool, the membrane-associated urea detergent, and finally the formic acid, which has most of the insoluble or the fibrillar A beta. We then digested each one of them with lysine instead of trypsin, and then we did the proteomics, which gives us the two canonical C terminus, X240 and X242, mid-domain, and the differentially truncated N terminus of A beta. This is the two-dimensional LC-IMS-MS of endogenous A beta 1 to 15 present in the Alzheimer's brain. On the top panel, you can clearly see this is the HPLC, and in the red is the different conformers of, if I may say, the A beta 1 to 15. And in the bottom panel, the different synthetic epimers that we had spiked into the homogenate. You could clearly see that in the red, the native number 1, that is 17L asp, is not the unique conformer, neither is the major constituent. Rather, number 10, which has both of the aspartic acid 1 and 7 isomerized, is the major conformer of A beta 1 to 15. Similarly, in the gas phase, there are quite distinguishable features in between these epimers. Compared to the native, the black one, if we have an isomerization or racemization at the N terminus, that is one aspartic acid, we do not see a significant change. However, when there is an internal isomerization, that is aspartic acid 7, racemization or epimerization or isomerization, we see a significant change in the conformation of the peptide. So this peptide can be separated both on the HPLC as well as in the gas phase. This is the two-dimensional LC-IMS of 4 to 15. In the top panel, in the red, is the endogenous, derived from Alzheimer's brain, and we can clearly see that there are three different conformers: the normal native L, the iso L, and iso D aspartic acid 4 to 15. However, in the gas phase, the behavior is a little bit different compared to the 1 to 15. Compared to the native black one, the iso and the iso D are more compact and they have a different CCS compared to the native. So we asked, what is the difference between the total amount of A beta present in the human brain? We quantified the total and we could clearly see a significant increase in all the different pools of 1 to 15 compared to the controls. We also observed the same kind of 10 to 12-fold increase in 4 to 15 as well as 1 to 15. Even in TVS, both 1 to 15 and 4 to 15 were significantly increased in Alzheimer's. We then asked what is happening to the normalized ratio of these isomers in the human brain. We could clearly see that there was a significant decrease in the native form, whereas the isomerized versions were increasing in all the different biological pools, even in the soluble pool. The same observation was made for 4 to 15. However, in the formic acid, there was only significant increase for the isomerized version as well as in the sodium carbonate. This is a pie chart which shows us what's happening in the brain in different pools of A beta. From the 1 to 15, we can clearly see that higher the solubility, that is the TBS, it has less modified A beta, whereas insoluble A beta is more modified, that is, it has more isomerization. Same is observed for the controls, but the fraction is less modified because it has less amount of A beta. Similarly, for 4 to 15, we could clearly see that there is higher isomerization in the insoluble fractions and the membrane fractions, whereas the TBS is less modified. That is, there is more native isoform of that peptide. So in summary, we can clearly say that the N-terminus isomerization or epimerization leads to a conformational change that makes it distinguishable in the liquid phase as well as in the gas phase. There is a distinct compartmentalization of the older A beta in the insoluble versus the younger modified A beta in the soluble pool. And the most important take home message is that there is a higher extent of isomerization of A beta in sporadic brains that makes it biochemically different. That is, the plaques that we see in the controls are not that as old as the ones in Alzheimer's. These isomerized A beta can serve as very good biomarkers if they can be found in the CSF or in the blood. And most importantly, in future, selective immunization of these against these modified isomerized A beta would be better for designing better therapeutic antibodies. And finally, I would like to thank everyone for listening to the talk and all the people that has helped me throughout this journey. Thank you very much.